Equivalent circuit and Phasor diagrams. Similarity between induction motor and transformer. The transformer and induction motor have some similarities, which have been noticed earlier. In both the cases, the mutual induction plays the key role. Transformer has a primary and secondary, whereas the stator and rotor in the induction motor. The secondary is connected to a load which draws electrical power. But in the case of an induction motor, secondary or rotor is short-circuited. The frequency in it is SF and the electrical power is converted to mechanical power. The similarities and differences between the two are shown in the table. Keeping the above points in view and the equivalent circuit of the transformer, the equivalent circuit of the stator of the induction motor is as shown in the image. The stator of the induction motor is represented by an equivalent circuit as shown in the image. Note the similarity between the primary of the transformer and the stator, where R1 is stator resistance per phase, X1 is stator reactance per phase. R0 is the shunt resistance, which represents the iron loss in the stator core. Its reciprocal Z0 equal to 1 by R0 is called conductance. X0 is the shunt inductive reactance, which represents the magnetic current I mu. Its reciprocal B0 equal to 1 by X0 is called susceptance. V1 is applied voltage to the stator. When the motor delivers no power output, the input is equal to the stator losses only. No load current equal to I0, where IC is core loss component. I mu is magnetic component. On similar lines, the equivalent circuit of the rotor can be developed. Note the similarity with the secondary of the transformer. Equivalent circuit of the rotor. The rotor may be represented by the following circuit, dividing both the numerator and denominator with S. It is given as the resistance term R2 by S could be split into two parts. The first term R2 is rotor resistance. The second term represents an equivalent resistance for Pm equal to mechanical power developed. When I2 flows in it, its copper loss is from the interrelationships of losses. Pm equal to mechanical power developed. Therefore, the equivalent circuit of the rotor is shown in the image. If the turns ratio K is K equal to N2 by N1 equal to turns per phase in rotor by runs per phase in stator. The rotor parameters can be transferred to the stator as in the case of a transformer. Then the exact equivalent circuit can be obtained as shown in the image. In the equivalent circuit, rotor resistance transferred to the stator equal to rotor reactance transferred to the stator equal to. As in the case of transformer, the shunt admittance branch can be shifted to the left extreme without committing much error. Then the approximate equivalent circuit can be designed as shown in the image. Maximum power in synchronous watts and maximum mechanical power development. The approximate equivalent circuit is drawn as shown in the image. Power developed in synchronous watts in the rotor input power is given by torque developed in synchronous watt equal to rotor input equal to rotor copper loss by S equal to cross output power into Pm by 1 minus S equal to Pi. To get maximum synchronous torque, maximum gross torque, R2 by S is taken as the load. And by using the maximum power transfer theorem, the condition for Pi to be maximum is given as let Sm be the slip obtained from the above equations. at the slip Sm given above, the maximum gross power developed is obtained. Maximum gross torque in synchronous watts. For finding the maximum power output, rewrite the equivalent circuit splitting R2 by S as two components. The mechanical power developed equal to: when a load resistance is equal to the Thevenin or Norton resistance of the network, supplying the maximum amount of power is dissipated by a load resistance. If the load resistance is lower or higher than the Thevenin or Norton resistance of the source network, its dissipated power will be less than maximum. Treating RL dash equal to RS dash into 1 minus S by S as a load, and using the maximum power transfer theorem, the condition for maximum power output or maximum mechanical power developed is given as, where n is the speed of the rotor. Phasor diagram. The vector or phasor diagram of the induction motor is as shown in the image, which is more or less similar to the transformer with the following exceptions. The magnetizing current is nearly 30% to 40% of full load current in the induction motor, while in the transformer it is about 3% to 5%. In the magnetic circuit of the transformer, there is an air gap. Because of high reactance of the air gap, much higher I mu is needed. If there is no air gap in a transformer, then its I mu is very low. The power factor of the induction motor is always lagging, whereas in the transformer, power factor depends on the nature of the load.